In physics, particularly in quantum physics, a system observable is a measurable operator, or gauge, where the property of the system state can be determined by some sequence of physical operations. For example, these operations might involve submitting the system to various electromagnetic fields and eventually reading a value. In systems governed by classical mechanics, any experimentally observable value can be shown to be given by a real-valued function on the set of all possible system states. Physically meaningful observables must also satisfy transformation laws which relate observations performed by different observers in different frames of reference. These transformation laws are automorphisms of the state space, that is, bijective transformations which preserve some mathematical property. Quantum mechanics. In quantum physics, the relation between system state and the value of an observable requires some basic linear algebra for its description. In the mathematical formulation of quantum mechanics, states are given by non-zero vectors in a Hilbert space V and observables are given by self-adjoint operators on V. However, as indicated below, not every self-adjoint operator corresponds to a physically meaningful observable. For the case of a system of particles, the space V consists of functions called wave functions or state vectors. In the case of transformation laws in quantum mechanics, the requisite automorphisms are unitary linear transformations of the Hilbert space V. Under Galilean relativity or special relativity, the mathematics of frames of reference is particularly simple, and in fact restricts considerably the set of physically meaningful observables. In quantum mechanics, measurement of observables exhibits some seemingly unintuitive properties. Specifically, if a system is in a state described by a vector in a Hilbert space, the measurement process affects the state in a non-deterministic, but statistically predictable way. In particular, after a measurement is applied, the state description by a single vector may be destroyed, being replaced by a statistical ensemble. The irreversible nature of measurement operations in quantum physics is sometimes referred to as the measurement problem and is described mathematically by quantum operations. By the structure of quantum operations, this description is mathematically equivalent to that offered by relative state interpretation, where the original system is regarded as a subsystem of a larger system and the state of the original system is given by the partial trace of the state of the larger system. In quantum mechanics, each dynamical variable is associated with a Hermitian operator that acts on the state of the quantum system and whose eigenvalues correspond to the possible values of the dynamical variable. For example, suppose as an eigenket of the observable, with eigenvalue, and exists in a d-dimensional Hilbert space. Then equals this eigenket equation says that if a measurement of the observable is made while the system of interest is in the state, then the observed value of that particular measurement must return the eigenvalue with certainty. However, if the system of interest is in the general state, then the eigenvalue is returned with probability. One must note that the above definition is somewhat dependent upon our convention of choosing real numbers to represent real physical quantities. Indeed, just because dynamical variables are real and not unreal in the metaphysical sense does not mean that they must correspond to real numbers in the mathematical sense. To be more precise, the dynamical variable, observable, is a Hermitian operator in a Hilbert space and thus is represented by a Hermitian matrix if the space is finite dimensional. In an infinite dimensional Hilbert space, the observable is represented by a symmetric operator, which may not be defined everywhere. The reason for such a change is that in an infinite dimensional Hilbert space, the operator becomes unbounded, which means that it no longer has a largest eigenvalue. This is not the case in a finite dimensional Hilbert space, where every operator is bounded, it has a largest eigenvalue. For example, if we consider the position of a point particle moving along a line, this particle's position variable can take on any number on the real line, which is uncountably infinite. Since the eigenvalue of an observable represents a real physical quantity for that particular dynamical variable, then we must conclude that there is no largest eigenvalue for the position observable in this uncountably infinite-dimensional Hilbert space, since the field we're working over consists of the real line. Nonetheless, whether we are working in an infinite-dimensional or finite-dimensional Hilbert space, the role of an observable in quantum mechanics is to assign real numbers to outcomes of particular measurements. This means that only certain measurements can determine the value of an observable for some state of a quantum system. In classical mechanics, any measurement can be made to determine the value of an observable. Incompatibility of observables in quantum mechanics. A crucial difference between classical quantities and quantum mechanical observables is that the latter may not be simultaneously measurable. This is mathematically expressed by non-commutativity of the corresponding operators, to the effect that this inequality expresses a dependence of measurement results on the order in which measurements of observables are performed. Observables corresponding to non-commutative operators are called incompatible.